So we really want to use limits to establish some information about series. So we want to know our series. And at this point now, we've looked at a whole bunch of series. Okay. And again, the first step is that if a series have any chance of converging, the sequence must have a limit of 0. So it must tend towards 0. Okay, so we want to be able to compare series with each other. So we should have some sense of which ones converge and which ones diverge, and have some references that we can always go to. So our main references are going to be these ones here. So our infinite geometric series, we did this in grade 12. Our infinite geometric series always converges as long as the R value is between -1 and 1. And the limit is always going to be this formula here, a over 1 minus r. So infinite geometric series, when the terms get smaller and smaller, they always are convergent. Okay, so that's one of our standards we're going to use. So we're going to have some other standards as well. This harmonic series is very important because that harmonic series is divergent. And that is our boundary series between converging and diverging series. Okay, and the P series then highlights that because when P is equal to 1, it's divergent. When P is greater than 1, we have convergent series. For example, 1 over n squared. The basal series is convergent. We also know, and I'm just going to add this into the notes, we also know that if P is less than 1, okay, so 1 over n to the P root, like that, root P. Let's zoom in a little bit and write that a little bit more clearly. Okay, so if we have it look like this, our series, when P is a root, okay, or in this case the P series is less than 1, we know that this is divergent, okay, because it goes to 0 slower than the harmonic series. Okay, so that's divergent. Okay, so that's also a standard we want to be able to establish. The other one is the alternating harmonic series is convergent. Although the harmonic series is divergent, when we alternate the terms, so we go from 1, okay, plus 1, minus half, plus a third, minus a quarter, and then we go back and forth, back and forth, back and forth, that converges to some limit. Okay, that eventually converges to some limit here. In fact, we know what this limit is, okay, this limit, and not that that value is actually significant for our purposes, but somebody has actually figured out that limit, and that limit's about 0.7 or log 2. Okay, so these are some established standards. Okay, these are very important then because these are going to be our standards of which we can kind of relate things to. Our infinite geometric series converging when R is between -1 and 1. Harmonic series is our standard, is our kind of a boundary series where things that converge are going to have numerators more powerful. For example, when P is bigger than 1, and they're going to diverge when the numerator is less powerful or P is less than 1. Okay? And then lastly is our alternating harmonic series. And we can see that alternating harmonic series are convergent. And we're going to look at some other alternating ones, and we can actually establish something a little bit more than just alternating harmonic series are convergent. So we can then now start using these series to determine whether things are convergent or divergent. Okay, we've kind of done this a little bit before, and we've done this informally. Okay, this is a comparison test. We're actually going to start naming these strategies now. So this is a comparison test where we're going to compare 1 over a over root n, and we're going to say that this is divergent, and we're going to compare this to a diverging series. So if we want to show something's divergent, we want to show that it behaves like another divergent series. So what we're going to do is this. We're going to say that we know that 1 over n is always going to be less than, we're going to say a over n. A over n is always going to be less than a over root n. Okay, for all n values, that's going to be true. So what we can then say is that because 1 over n, sorry, a over n, as n goes from 0 to infinity, we know that this is divergent. Okay, so we know that this is infinite or divergent. Therefore, by comparison, this is a comparison test. We're now giving this test a name. By comparison, we can say that as n equals 0 to infinity, a over root n must also be divergent. Okay, this is our conclusion. And this a is actually a distractor because really that a, since it's on every term, that a can actually be factored out. So this is equivalent to a 1 over n. Okay, these are equivalent to each other. So we can actually make the argument without the a. So looking at that next one, we can see that we can make some conclusion about the convergence or divergence of this. So just pause for a minute and think, does a over log n converge and diverge? And why do you think that's the case? Okay, so this series actually is a diverging series. Okay, so this diverges. And the reason why we should think that is the denominator is weaker than our diverging series 1 over n. Okay, remember, that's our kind of our boundary series. So what we can say is this. We can again make this argument. A over n is going to be less than a over log n. Okay, therefore, since 1 over or a over n diverges, okay, we know it's infinite, we can make the conclusion then that this series, which is going to be bigger, we can claim that this is also divergent. Okay, and we've done a comparison test. Okay, and this is it is a little bit informal. There's not, we have to make some statements and justify it, but really all we're doing is comparing them. Okay, and as long as you can kind of justify that comparison, we don't really need to write a huge formal argument for that. So why is this one a divergent series? Okay, well, this one here, why is this divergent? Well, it's kind of hard to tell because we don't know what that is, but we can kind of guess that this is divergent because it's a root and the root is going to get even bigger. So that should be weaker than like even a square root series. But in fact, we can even just look at the very first criteria. Does an go to 0? And that's not true, it doesn't. Okay, so we can make this test. We can just say a to infinity is equal to limit as n goes to infinity of a over root n over n. And we've already established that root n over n as n goes to infinity is 1. So we know that this is equal to 1. That means that the nth term is not equal to 0. Okay, so an does not tend to 0. It goes to a. Therefore, it does not converge. It cannot converge. So we should make actually this statement. We should make, therefore, the sum of those terms cannot converge.